Cool cats and kittens. It's Mikhail here to present my individual project over shear deformations, fabrication errors, and temperature changes. So I'm going to jump straight in to what changes I've made to the input files. Let's start with a frame because it incorporates all three and has all the information on there. And so first, after you have defined the in-span loads, there's now an option to define fabrication errors, and those definitely come in two different flavors. So the first is that a member is either too long or too short, and that's going to induce some axial forces. And so after specifying the element number and telling the code that this is a axial fabrication error, you can specify by how much it is too long or too short. And then the fourth column is just set equal to 0. The fourth column is only for type 2. Type 2, speaking of, is if the member is bent. And so when it's bent, that's going to induce bending moment as well as some shear forces. And so after specifying the element number, you can tell the code that the fabrication error is a straightness error, and it is defined positive if the bend is in the negative local y-axis. And what that looks like is this right here. So positive if the member is too long, positive if the bend is below the local x-axis, if the error is in the direction of negative local y. And that is just so that the moments that are generated are going the correct way. It's actually rather arbitrary. Down here, the fourth column for type 2 specifies where the bend is occurring. If it is in the midpoint, then there will be no shear generated, but if it's off to either side, then there will be some shear forces induced, and so that's kind of an important value. Moving on to temperature changes, the only thing that needs to be specified here is what element this is occurring on, the temperature at the top surface, and the temperature at the bottom surface. If there's no temperature changes, you can just leave it blank. Down here, we have some new element properties that are needed in order to implement these new special topics in order. For shear deformations, you have to specify the shear modulus of each member. And once you do that, that is an indication to the code that you want to include shear deformations in your calculations. Additionally, there's this new value, A shear, which is the shearing area, which is different from the gross area of the section. And this just allows for some more accurate analysis of wide flanged members, so like the W shapes in steel, where the web is the only part that's actually resisting that shear force. Additionally, there's a new shape factor, so this is the shear shape factor, and it's 1.2 for rectangles, and in my report I actually included some other shear shape factors for circular beams and for wide flange members. The only thing you have to be careful of, again, is that for wide flange, it's only the area of the web, not a gross. For temperature changes, you need to specify the coefficient of linear thermal expansion, alpha, and as well as the depth, and that's just for calculating the induced bending moment in frames and beams. For trusses, everything is essentially the same, except you can only have type 1 fabrication errors, and temperature changes are only going to induce axial forces. And for shear, there's no shear in trusses, and so it just needs to be left empty. For beams, you can only have a type 2 fabrication error. You can only have bends because there's no axial forces in beams, at least the way that they're modeled in here. Temperature change is the same. Down here, we don't need a gross, that's only for frames, but we still need the shearing area, the shape factor, and the depth to be specified. So let me jump into how these special topics were implemented into my code. Starting with the driver, which is just from the group project, nothing has changed all the way up until we get to generating the element stiffness matrix. So when we generate the element stiffness matrix, we now need to check if shear deformations are being considered, because that will modify the little k for each element. So if you've specified a shear modulus, that's an indication to the code that shear deformation should be included, and that means that we're going to go ahead and calculate beta s, which is 12 EI Fs over G A shearing and L squared. Otherwise, if you don't want shear deformations and you haven't specified G, it's just going to set that equal to 0, which effectively ignores all shear deformations. So down here, the only thing that's changed in order to implement shear deformations is that when we're calculating KFU, KMU, KM theta, all of those stiffness values, we're now multiplying by 1 over 1 plus beta s. For KM theta and for K hat, there's an additional term here But other than that, and in one you're adding and in one you're subtracting, other than that, that's it for shear deformations. It was pretty easy to implement. For the other two special topics that have been implemented, that's going to take place when we're generating our equivalent load vectors. And so that's QFE and FFE. And so after we've done all of our regular in-span loads, we're going to get down here, and I've called a new script called fabrication errors. And fabrication errors, we're going to split it up by the two different types. Case 1 where it's too long or too short, and case 2 where it's a straightness error. For type 1, what we're going to do is just multiply the axial stiffness of that element by the deformation needed to like push that fabrication error back. And so it's just like a 1D spring, essentially, which is what we started the semester with. Super simple. For straightness errors, the only thing that's different here is that we're going to calculate the theta B and theta E. Those are the two different nodes on either end of the member. And that's going to be the chord pointed from the B vector down to this point down here, and the chord from here to here. And you can see how there would be two different angles there. And so those are technically deformations on beams. And so we can take those displacements and multiply on the left by the little k matrix to get a QFE. And that's just going to be added to the QFE that we calculated for any in-span loads. And the only difference between beams and frames are where these values are being included. So again, pretty easy. After we've done fabrication errors, I've created another script called temperature changes. In here, what we're going to do is loop through that temperature change input variable. And what we're going to do is, if it's a truss or frame, calculate the axial force caused by that temperature change. If it is a beam or a frame, we're going to calculate the bending moment. And those are just some equations that Dr. Byerly derived in her videos, and they just need to be inserted in the QFE vectors where they belong. And so, again, this is just a short little script to include temperature changes in the group project code. Pretty easy. For verification of the program, shear deformations, this is the example Dr. Byerly gave, and I've compared my values with the expected values that she provided for us, and everything lined up perfectly. And so I know that this implementation of shear deformations is 100% correct. And again, it's so easy that it would be pretty impressive if you messed it up. Sorry, that's not a dig at anyone if you did mess it up. Things are difficult now with coronavirus. Anyways, so for fabrication errors, the way that I validated these, I did an example. This should look familiar. It's from homework T1. It's the truss homework that we did with all of these vectors worked out. And the only thing that I did was I calculated QFE for each element due to, in this case, all three elements being 1 inch longer than they should be. And so I calculated a new DF and PR, and I compared those to the values that my code gave, and the hand calculated matched the code values just fine. Then I verified type 2 errors on the beams, essentially the same way, just calculating theta B, theta E, creating the QFE vectors, and then checking with my code output. Same thing, everything matched. For frames, I first did a frame with just a type 1 error, where this horizontal element was 1.5 inches shorter than required. And I verified that with my code. And then I made things real complicated. And I decided to do a type 1 and type 2 fabrication error. So now this member is 1.5 inches shorter, and this member, it has a straightness error at the midpoint. And so that just makes it a little bit more complicated calculating the QFEs. And so, let me go back. Yeah. So here's the straightness error addition to the QFE, and here's the axial fabrication error addition to the QFE. And once we calculate these values, we can compare it to my code. Everything was good there. So you can have multiple fabrication errors in your structure of different types, and the code will handle it just fine. For temperature changes, the code is pretty common for all three structures, so I only checked with a frame because that will have both axial and bending moments. And so here's the addition of the temperature change to that QFE vector. That's really the only thing that's changing in the entire process for calculating or analyzing the structure. Got some new DFBRs, checked them, everything was good. So that brings us to the last part of this video where I'm going to talk about the independent analysis I did over when shear deformations are considered negligible. This is important because in pretty common actually in structures you have a lateral moment frame, say in like this concrete frame that we have here, and we can have what's called a transfer girder where you have a column that connects in the middle of a beam. And so that means that this beam has to accept a pretty heavy concentrated load right in the middle, and that means that these members can get pretty massive. And so when they get that large, they're considered deep beams, and you actually need to include shear deformations in your analysis because we're basically there's like a spectrum from beams to shear walls, and these deep beams are somewhere in between. And you can kind of tell that this beam is going to shear as well as bend. So those both need to be included. And so the model that I did was a fixed beam with a distributed load that kind of represents the dead load from the self-weight of the beam, as well as a concentrated load right in the middle, which is kind of like this column up here. And so I basically create a new input file for these factors and this geometry, and the only thing that changes basically the dependent or independent variable in this experiment was the length of the beam. And so the depth stays the same, but the length changes. And what that means is that your LH ratio ends up changing. And so here's kind of the results of my little analysis. I analyzed a bunch of different LH ratios, increasing all the way up, both with shear deformations and without shear deformations. And you can see that they originally start with a huge difference. But as that LH ratio gets larger and larger, basically as the beam gets more slender, the effect of shear deformations becomes really small. And a different way of looking at it is kind of the percent error between the two different cases, the two different ways of modeling the beam, considering that the shear deformation analysis is technically a bit more accurate. But you can see that once you get to about an LH ratio of 10, the percent error is only 10.3% in this case. And so 10% error in a structural model that already has a bunch of error from calculating loads to the material properties to even the model of how you're calculating shear deformations. 10% error is not that bad. And so once you get above this point, that error goes away to being negligible. Yeah, and so that's what I did for this individual project. I hope you enjoyed watching my long-winded video, and hopefully it wasn't too boring. But thanks for watching.